Hello, thank you for coming to this presentation today on graphs and networks. I'm Charles Poe, Senior Kernel Developer at Wolfram Research. I would like to start this presentation by giving a brief historical perspective, followed by some core concepts of graphs and networks. We will focus next on modeling, which will be put to work to understand and analyze graphs and networks with practical examples using Mathematica. We live in a connected world, and each day create millions of connections through social media, Facebook, LinkedIn, Google+, Twitters. The result are vast and complex network of connections that link people to other people, document, location, concept, creating an evident and pressing need for powerful tools and theory to collect, analyze, visualize networks, and generate insights. In the past few decades, researchers have developed innovative mathematical techniques and applied graph theory for network analysis. The first known application of graph theory was earlier treatment of the bridge of Königsberg. Starting in the late 1960s, several scientists such as Stanley Milgram, Watts, Trogas, and Barabasi used graph theory to model social networks. As network science became a scientific discipline of its own, and network models were used in physical, biological, and complex systems, an increased number of softwares and tools continue to be developed for modeling, analyzing in each field, domain, and application. Mathematica, in addition, provides a whole new way to model networks and analyze graphs with its unique integration of concepts across disciplines, everything from mathematics, computer science, physics, to biology, social network analysis, economy, and many more. Graphs and networks are fully integrated into Mathematica, with great features, high-performance scalable data structures, advanced aesthetic, broad modeling and analysis capabilities. Let's start by looking at the concept and ideas behind graphs and networks. A graph, in its simplest form, is a collection of points joined together in pairs by lines. In graph theory terminology, the points are referred to as vertices and the line referred to as edges. The relationships between vertices can be conceptualized in terms of pair of vertices. A network, on the other hand, is a graph that represents something real, with a structure and a behavior. The structure is modeled easily and effectively by graph theory. Vertices, also called nodes in this context, may be web pages or router for the internet. Edges or link are hyperlink between web pages or cable between routers. The dynamic portion of a network can be seen as a set of micro-rules that govern the behavior of nodes and links. The internet, social networks, biological systems are growing and changing networks. One must understand a dynamic property in order to fully understand these systems. Now, let's look at the graph representation in Mathematica. Graph can be constructed using the function graph. This function takes a list of edges and vertices as argument. A special typeset character has been introduced to represent undirected edges. The resulting object is a plot or a graphical representation of a graph, which can be used as input. Here we compute back the edge list, or as output in program or in document. Moreover, you can change the appearance of a graph by a simple click of a mouse. The resulting manipulated graph is still a computable object. The same constructor graph is used to build directed graph. A list of directed edges or rules can be given as input. A special typeset character is also available for directed edges. Both directed and undirected graphs are treated uniformly throughout Mathematica. One of the most important things to remember is that the graph object is treated as a row object for purposes of pattern matching and efficient representation. We internally use several representations such as sparse array or double linked list to efficiently store and manipulate graphs. Instead of using the head of the expression to check if it's a graph, you can use GraphQ or other Q functions such as undirected GraphQ or directed GraphQ. Also, you can't access part of a graph using first or part. You should use vertex list to get the list of vertices, edge list to get the list of edges, or option to get all additional parameters of your graph. Moreover, information can be attached to each graph, vertex, or edge through a flexible and user-extensible property framework. Properties such as shape, label, weight, style for vertices or edges can be used for both visualization and computation. You can change the style of a vertex using the property vertex style for all vertex or a specific vertex. All graphic options such as image padding are supported, so you can customize graphical representation of your graph. Vertices and edges can be labeled using vertex label, edge label, and label style can be modified using vertex label style or edge label style. User property can be attached to an edge or a vertex. Here, we are adding a property strength to edge 1 to 3. You can use the function property value to query and extract those properties. All this information are stored in your graph option. Graphs have several representations. One of the most important ones is the adjacency matrix. This representation, combined with mathematical metrics and optimization framework, allow taking advantage of multi-paradigm approaches to graph programming. Graph can be built from matrices. Here, we use adjacency graph to build a graph from a given matrix. Adjacency matrix allow to convert back to a matrix. Additional matrix representation, such as incidence matrix, Kirchhoff matrix, are also available. Modeling plays a prominent role in several disciplines. Network models are used in several disciplines. In computer science, network models are used in database design, data mining, or web mining, for example. In business informatics, organization diagram, event-driven process chains are described as networks. Gathering data and extracting the relational structure from experiments, simulation, and data source is critical for modeling in all these areas. Mathematica automatically handles hundreds of data formats and subformats, all currently integrated through Mathematica uniform use of symbolic expressions. Graph and network can be directly imported into Mathematica from .dot file, project file, GraphML files. In addition, built-in functions such as morphological graph allow to construct graph from image or other data sources. In this example, we import a map of a city from Wolfram Alpha, and we use morphological graph to transform the image to a graph. The function neighborhood graph can be used to identify the city block, and we use highlight graph to highlight the result from neighborhood graph. Mathematica also have built-in extensive collection of theoretical graphs and empirical networks. Graph data contain more than 6,000 graphs with hundreds of properties. Most common empirical networks and graphs are available in example data. Here, we show a network of books about US politics. This graph can be directly manipulated, insert in notebook, document, or used as input for computations. Random graph provides an excellent tool for studying the structural feature of networks and a convenient basis for further modeling work, such as the spread of disease over contact network or terrorist networks. A random graph is a model network in which some specific set of parameters take fixed value, such as the number of vertices or the number of edges. Yet the network is random in other respects. The theory of random graph began in the late 50s in several papers by Paul Erdos and Alfred Remy. In the late 20th century, the notion of 6 degrees of separation, popularized by the 6 degrees of Kevin Bacon, inspired Strugars and Watts to define the small world random graph. At about the same time, it was also observed in social networks and on the internet that the number of neighbors of an individual or computer follow a power law distribution to define the preferential attachment model, which had this property. All these models are immediately accessible in Mathematica. Combined with Mathematica probability and statistical functionality, simulation and analysis of networks are now within everyone's reach. As businesses, entrepreneurs, engineers, and government agencies alike are looking at network analysis tools for insight, information visualization becomes an important component in network analysis. Mathematica brings a high level of algorithm automation and computational aesthetic to graphs and network visualization, with a convenient symbolic mechanism for creating, labeling, and styling graphs. In the example below, we build a UML diagram, state diagram, using the graph object in Mathematica. Here, we use the shape function of graph as well as labeling to actually lay out the state diagrams. The resulting object is still a computable object. For example, we can compute the shortest path from start to an end. In the example below, interactive effects are attached to vertices and edges in the food web, which provide information drill down for greater information visualization. With a couple of lines, you can get an interactive web directly linked to Wolfram Alpha extensive data collection, ready to be exported in CDF for presentations. In this example, as you see, we list our edges and we do a call to Wolfram Alpha and then define the shape we want to actually see in our graph. They can be image or any expression in Mathematica. They can even be a direct stream from a camera. And after that, all you have to do is wrap graph around those arguments and evaluate, and you get a graph object, an interactive graph object. Multiple scientific disciplines have come together to contribute techniques and perspective in an effort to understand how networks operate. The resulting research effort exhibits an intriguing blend of different flavors. What we provide in Mathematica is a unified computational perspective on graphs and networks. In the next slide, I will present a small set of hundreds of functions available in Mathematica for graphs and network analysis. An overview of the collection of functions we have available in Mathematica can be found in our guide pages. We cover construction of graphs, representation of graphs, styling, labeling, and layout of graphs, operation and modification of graph, predicate and property such as isomorphic graph Q, measure and matrix, path and cycle, component and connectivity computations, click, cover, and independent set, as well as graph programming. Structural properties of vertices and edges are key ingredients in graph analysis. Local structural functions such as sample graph Q and directed graph Q allow testing as to whether a graph is sample or directed. Fast and efficient algorithms for graph isomorphism, connectivity, and much more can be used for understanding the global structure of a graph. One of the key problems in graph is navigation, in particular finding the shortest path between two vertices, navigating a road network, or finding the way out of a maze. In the example below, we use the function find shortest path to find our way out of a maze represented as a graph. We can highlight the resulting path using highlight graph function. The length of the shortest path gives rise to a whole collection of natural measures such as diameter of a graph, as well as graph center. If instead of navigating from one vertex to another, you will like to traverse the whole graph in some way, you are looking for cycles. Our function find the Lorentzian cycle and find the Hamiltonian cycle provide paths that traverse every edge or vertices of a graph. Mathematica supports a broad range of measures that characterize graphs, from simple measures such as the number of vertices and edges that tell the size and the sparsity of a graph, to vertex degree, which tell you how locally well connected each vertex is. Other measures include the geodesic distance in a graph or centrality measure that give a measure of how central in the whole graph each vertex is. In the example below, we use the betweenness centrality to actually find the 10 most traversed stations in the London Underground along the shortest path. So we represent our London Underground as a graph, and then we compute the betweenness centrality using betweenness centrality functions, as well as a combination of highlight graph to actually illustrate and display those most traversed stations. An important property of a network is its connectivity. Is there a path from every vertex to another vertex? In the example below, we look at the ENRON email communication network. The data is publicly available, and we import it using our import functions as a text file. We do some basic parsing on the text file using string split, and then directly apply graph to build the actual ENRON email communication network. From there, we can do some basic statistics as finding the number of actors, the number of email exchange. Look at the largest connected component, how many actors are in the largest component, how many emails have been exchanged between them. All this by just using vertex count, edge count, as well as connected component. For social network, one is often interested in the kcal component that indicate group of people connected in a limited way. The function kcal component provides this functionality. Highly efficient building Mathematica function provide connectivity functions from detection to analysis of connected components. By providing a completely extensible set of vertex and edge property, you can make a graph represent much more than the structural information and body in their topology. This property can also be used to store the state when scanning the graph in a depth-first or breadth-first manner, as used by many algorithms. The function breadth-first scan and depth-first scan have a whole flow of events, such as finding frontier edges or discover visited vertices. In the example below, we look at the depth-first search path on a grid graph by just using the event frontier edge as well as saw and reap function in Mathematica. Highlight graph allow us to actually visually see the path we traverse. A big part of what we do in Mathematica is to democratize knowledge. We want more and more people to take advantage of graphs and networks than ever before, to do next generation simulation, modeling, and analysis. You don't have to be a researcher or an expert to use graph and apply it to your work. Mathematica is unique in offering an extensive and fully integrated environment for modeling and analysis of graphs and networks. We will continue to add the state-of-art functionality for all areas, from mathematics, physics, computer science, to biology, social network, economic, and marketing. Thank you very much for your time today.